so let's get started with differentiation. We're going to start with the real basics. Now, what exactly does the derivative do? Graphically, the derivative just points out the gradient of the tangent of a curve at any given point. So we can see over here, we've got this curve that goes like that. At this point over here, if I were to draw a tangent just looking at the gradient of the curve, we can draw that out. And that is the derivative. That's what the derivative can help with as well. Okay. Oops. Okay, so now let's go through the actual rules. So this is the very basic rule. So the differential of x to the power of n, we bring that n down to the front, so we times it as a coefficient, and then we reduce that power by 1. Okay, so the simple one, let's say it's like 3x squared. Then if we're going to derive, it's equal to 3 times 2 times x to the 1, which is 6x. Okay, that's how we use that rule. I'm going to assume that most of us know this at the very least because it was also taught in year 11, but let me know if not. Okay, then we have the differential of trig functions. I personally don't even remember what we went through last holidays, but I do remember a lot of you guys hadn't gone through trig differentiation. But yeah, I don't think I'll have enough time to like draw the graph thing because I did that last time as well. But it's also in your formula sheet that the derivative of sine x is cos x, the derivative of cos x is negative sine x, and the derivative of tan x is sec squared x. Okay, we'll be going through a lot of formulae in the start. It won't be super duper interactive, but we just need to get all of the basics done first, okay? Now we have the exponentials. The derivative of e to the x or e to the f of x is a dupe. It's probably the first one that you guys learn apart from the actual rule itself. And that, if we're going to do it properly, it's e to the f of x. So derivative of that is f dash of x times e to the f of x. Okay. Then we have this disgusting formula. I personally would not recommend you guys to memorize this because in the HSC you'll receive like 1, maximum 2 questions on it, and it's in your formula sheet and you'll rarely receive a question on it, as well as this one over here, this log one. I think I've received 2 questions on it in my life, and that was like in a textbook. Okay, so these two, know of them, know where to find them in the formula sheet. Don't worry about memorizing. This one over here though, super important to memorize. And that is the natural log of f of x is equal to f dash of x on f of x. Okay, so it's a pretty simple one, but a lot of people seem to forget it. But I want you guys to pay special attention to this, because when we start integrating, this rule, well, the inverse of this rule, is one that everyone forgets, and the HSC like waits for you to forget this. Okay. So then we have the chain rule, which looks a little something like this. So it's a function within a function, and we need to, I don't know how to explain it without a question. Let's say we have x squared plus 1 all cubed. So if we want to derive that, then we take the g, well, we'll go the f dash x first. So this is f of x inside the function. F dash of x is 2x times 3 x squared plus 1 squared. Okay, so that gets us 6x x squared plus 1 all squared. That's how it works. I personally am not too good with explaining how that one works though, sorry. Okay, then we'll just put them all together. If you wanted to take a screenshot of this, I'll give you like 5 seconds. So 5, 4, 3, 2, 1. Okay, we'll move on to the product and the quotient rule, aka the two rules that people always accidentally mix up together. But yes, so if we're taking the derivative of something that's being times by another, like two separate functions, so let's say it's like 2x times e to the x, so they're two separate functions, then you will need to use the product rule. And then the quotient rule would be like x plus 2 on x. Or yeah, you can use the product rule for that, the quotient rule for that, sorry. So yes, I'm hoping you guys are kind of familiar with this. If not, I'll just go through a question anyway. We'll do the quotient rule because that's a bit more of a tricky one. So let's say the question is e to the x on 2x, okay? So I will say that u, which is the numerator, is equal to e to the x. V, we'll do v over here. V is equal to 2x. U dash is equal to e to the x. V dash is equal to 2. Okay? So we're going to follow that same pattern. We're going to times by this first and then minus that. So ex times 2x minus 2ex. Oops, pressing all the buttons. All on 2x squared gets us to 2x ex minus 2ex on 4x squared. We'll take out a common factor of 2 and we get ex x minus 1 on 2x squared. Okay. That is how we use the quotient rule. I'm going to assume that everyone knows how to do this because most people have done differential calculus and you did it in year 11 as well. Okay, now let's do the application of differentiation. Now, once again, what does it properly mean? The first derivative is, as I was saying before, the gradient of the tangent at any given point. Okay, so that can be given in a range of like notations. So dy dx or d dx, f dash of x or y dash. Okay, and what it actually means, if f dash of a, so at any given point, is positive, then the gradient is positive, so the graph is increasing. Okay, if it's negative, then the gradient is negative and the graph is decreasing. If it's 0, then the gradient is 0. So it's called a stationary point. Okay, stationary point. That's an important word to know if you're not too familiar with it already. Okay, then we have the second derivative. Okay, so the first derivative tells us the gradient. The second derivative tells us the concavity. Okay, so concavity is like concave up, concave down. Okay, so it's basically the rate at which the curve is increasing / decreasing. So it's got the notation d squared y on dx squared, f double dash x or y double dash. So if f double dash a is positive, then it's concave up like a cup. And if it's negative, then it's concave down like a frown. And if it is 0, then it is a possible point of inflection. And I would like to highlight possible. Whenever we have something like that, we need to test before and after to actually show that it is a point of inflection, because sometimes it might not be. Okay, now I have a slider question for you. Okay, so just down below, let me know at which point on this curve are the first and the second derivatives both negative. I'll give you guys a few minutes. Got a couple of responses going through. I'll give you another minute. Okay, we'll wait till 40 if we can. Okay, Q. Okay, now let's show the correct answer. It's B. Good job, most of you guys. Now let's just go through this. So what does it mean for the first derivative to be negative? The gradient needs to be negative, so it needs to be decreasing. Now that takes out, well, I'll just circle which ones. So it's decreasing at B, it's decreasing at C, okay? Then it needs to be second derivative negative. So it needs to be concave down, like a frown, okay? So what does that mean exactly? You can see it a bit more clearly over here, where this is still increasing, but it's got a negative concavity. So here and here. So what like satisfies all of them? It's B. Okay. Now I was supposed to go through something, so let me quickly work it out. Okay. And now we'll just quickly draw a few things. Okay, so we have this, and then we have this, and then we have this, and then we have this. Okay, so if we take a look at the actual behavior of the curve in all of these oddly shaped pierres, I don't know what they're called, you can see over here that the derivative is positive, and so is the concavity because it's concave up like a cup. Okay, over here, we're still concave up, right? So f double dash x is greater than 0, and f dash of x is, it's negative, so it's decreasing, right? Okay, over here, we're still increasing, but it's like at a lower rate, right? So it's going concave down like a frown. Oh, sorry, increasing still. And a negative concavity. And over here, we're decreasing, and we're decreasing at an increased rate. So we're concave down like so, and with all, oopsies. Is negative, and so is this. Okay. Awesome. Okay, hopefully if anyone has any questions on this, just pop it in the Q&A. And just as I was saying, it's literally right on the slide over here. So when I'm going through, I'm always glancing and taking a look so that you guys can stop me whenever you need to. Okay, now as I was talking about, I highlighted a bit earlier, stationary points. Stationary points are when the gradient is equal to 0. It can either be a maximum turning point or a minimum turning point, or occasionally neither. There's ways to determine it. Two of them, well, yeah, there's only really two. So there's the table of values, which one of my students, like that just graduated, their school called I don't know if their school or just they call it the bucket hat test, and I like that, so I'm going to call it the bucket hat test as well. And then there's the second derivative test. And they both have their pros, they both have their cons, and we'll go through both ways just to see how everything, like what you prefer, because it's completely up to you. Okay, so we've got the table of values. Find the value of the derivative near the stationary point. So next to it, to the left, next to it, to the right. Okay, so we'll have like, obviously it'll look a bit nicer for you guys because you're not drawing on a screen. Okay, so we'll actually write proper numbers. So let's say Actually, no, I won't write proper numbers, but just know that they should have proper numbers. So x f dash of x, x f dash of x. Actually, I'll put real numbers. 1, 2, 3, and then 4, 5, 6. Okay, just showing as an example. So we'll put this is the turning point, this is the turning point, and this is -2 plus 2, and this is +4 minus 1. Okay, then we use the bucket hat test, and we see that this is decreasing, this is stationary, and this is increasing. Therefore, min TP at x is equal to 2, right? Because it goes like this, as opposed to this, where it goes increasing, 0, decreasing. So the bucket hat is down. So therefore, max TP at x is equal to 5. Okay? Perfect. When drawing a table of values, which values should you choose? How close to the number are you testing? How close to the number you're testing do they have to be? Ideally, the closer the better. Especially like if it's a really simple curve, that's only got like one stationary point and stuff like that. Sure, you can do like what I've done, like one number to the left, one number to the right. But if it's a more complex one, it's got like a few things going on, I personally would go as close as you can. So let's say like if the turning point was at 2, I might go 1.5 and 2.5. Or I could go even closer and be like 1.9 and 2.1. They're ideal, 1.9 and 2.1. They just won't be as nice of a number and a bit more difficult to put into your calculator. But ideally, best thing you can do, get as close to 2 as you can. I hope that answers that question. And then we have another question. Can't you simply just put the stationary point into the double derivative to find the nature of it? Yes, you can. That we will go through right now. Do you have to specify if it's a local or a global min point? Pretty much no, unless the question asks for it. But your teacher might want you to do a different thing. My teacher never told me to do that. So the HSC won't tell you to do that, but maybe your school might mark differently. But yeah, it just depends on what the curve looks like. You can never go wrong by saying whether it's a local or global minimum/maximum point. But yeah, just depends on the question and your school. Okay. Next one, so we need to find the value of the second derivative. If it's positive, concave up, or minimum. If it's negative, concave down, therefore maximum. Do they have an example? No, they don't. That's so annoying. I'll just make one up. So let's say it is x squared minus 2. Okay, that is my thingy. So f of x. So f dash of x is equal to 2x. Therefore, TP at x is equal to 0. Okay, now I need to find the nature of the turning point. I could do two things. I could do the bucket hat test that I just did before, or I could find the second derivative. So f double dash x will just be equal to 2. Okay, so at any given time, it is a positive concavity. Therefore, min TP at x is equal to 0. Okay, that's how that works. We'll go through more questions like that in the near future. Okay. Recall the points of inflection are where the concavity changes. Sometimes they could possibly be a stationary point as well. Think of like a cubic curve, so like this. Like this, it's got a horizontal point of inflection, it's called, if there is a stationary point and a point of inflection. So over here it's concave up, over here it's concave down. Or it could just be something like, oh, why is it so hard to think of one? Like that, literally like that. So right here is the point of inflection. On the left of it, it's concave up. on the right of it is concave down. Okay, stuff like that. That is a concavity change. But any given like time that you like, oh, I can't speak today, sorry. Anytime that you are looking for a concavity change, you do need to use the bucket hat test to figure out whether it actually is a concavity change, because sometimes it could be neither. Okay, so I'll show you some examples. So we have a concavity change. Looks like this. Okay, that's one. This is the other. And this is the other. Okay, so over here, we'll just write d squared y dx squared. So here's the point of concavity, here's the change of concavity, and here's the change of concavity. Okay, so initially we have a negative, a 0, and a positive concavity. Over here we have a positive, a 0, and a negative concavity. And over here, it's a bit of a special one. It's a positive, a 0, and a positive. Okay, so, oh, sorry, this is negative. So because there is a change in concavity in this one, it goes from negative to positive, therefore POI. Over here, there's also a change in direction, right? It goes from positive to negative, therefore POI. And over here, at that given point, the concavity is 0. However, there's no change in concavity. So therefore, there is no POI. Okay? Okay. Note that when doing a question, you should write the actual values. Yeah, so like I said over here, well, like I did over here, I did minus 0 plus. Minus 0 plus is not really what we should do. We should put proper numbers, just like I did over here. Put proper numbers in, and then put proper numbers into the answer over here as well. Otherwise, you're probably going to lose a mark. Okay. Yeah, so we'll use an example. Like so. So this is x, so f double dash of x, and we have 1.9, 2, and 2.1. Okay, and I've just made up some random numbers: 0.12, 0, negative 0.12. Okay, so this is concave up, this is 0, and this is concave down. Okay, so therefore we can say, oh, and like this is for an example where we're testing stationary point at x is equal to 2. And yeah, so this is just a scenario, by the way. I'm not using any specific numbers. But then you'll say, therefore, max t. I am so sorry. I don't know what I'm doing. This is supposed to be a derivative question, and I am not doing it. I am so sorry. It's supposed to look like this. It's a derivative question, not a concavity question. So max TP at x is equal to 2. Okay, sorry. I've just got like random notes on my side piece of paper, and I did not write them too well. Okay. Then we have if a stationary point happens to be a point of inflection as well. As I was saying before, it's a horizontal point of inflection. And I'm going to draw a nice Venn diagram to kind of put it all together. One circle, another circle. Now this is the y dx is equal to 0, and this is d squared y dx squared is equal to 0. Okay, so this is a concavity change, not like that quartic that I had in the previous slide. Okay, so this is a point of inflection. This is a stationary point. And when we put them together, and it's both a stationary point and the point of inflection, it is a HPOI, aka a horizontal point of inflection. Oh, it is really hot today. Okay. Yeah, so just over here, this would be a horizontal point of inflection. Okay. Yes, so all of this is useful for curve sketching, and we will go through that not today, but in the next lecture series where we put together our differentiation skills, integration skills, put it all together with our graphing skills, and we throw it onto a piece of paper. That's all for next time. But we can apply differentiation to go further than just curve sketching, okay? And we can use it for problem solving, okay? So let's go through a question right now. Okay, so a farmer wishes to make a rectangular enclosure of area 720 meters squared. She uses an existing straight boundary as one side of the enclosure. She uses wire fencing for the remaining three sides, and also to divide the enclosure into 4 equal rectangular squares of width x meters, as shown. We're given the total length of wire fencing, and we need to find the minimum length of wire required, showing why it's a minimum length. Okay, I'm going to give everyone 5 minutes to try this on their own first. It's not a Slido question, but I do want you to just take a while to think about this. Yeah, so 44 past, we'll go through it properly. Also, we've got some really good questions in the Q&A. Make sure once you're done with the question, if you do have any questions, pop it in the Q&A or just read through them and upvote the ones that you think are good. Okay, one more minute. Okay, let's get started. So this question's fairly simple because they've pretty much given a lot of the work in for us really, really nicely. We just need to find the minimum length required. Okay, so let's start going through this now. Okay, so given that L is equal to 5x plus 720 on x, we can find dl dx. Okay. Actually, let me just first rewrite this to make it a bit easier for differentiation. For those of you that aren't too confident yet. So it's plus 720x to the minus 1. Okay. So something on x is the same as x to the minus 1. Okay. dl dx will be equal to 5 plus 720 times. So we're going to take that down to the bottom. So minus 1 times x to the minus 2. Okay, so it'll be 5 minus 720 on x squared. Okay, now we want to make this equal to 0 because we need to find a turning point if we're looking for the minimum length. Okay, so we're going to say that 5 is equal to 720 on x squared. I'm going to times everything by x squared and divide everything by 5. AKA switch. I need a sneeze, but I don't need a sneeze. Okay. Switch to 5 and the x squared. So x squared is equal to 720 on 5, which my brain can't comprehend right now in holiday mode. It's 144. Now, yes, the answer to x is 12, but we first need to write that x is equal to plus minus 12. Okay, the reason being is because we all know by now, or at least we should all know by now, that we can square a negative number and get 144. Well, negative 12 and get 144. We can square 12 and get 144. So when we square root it, we can get plus minus, right? So we then need to say as length is less than or is greater than or equal to 0, therefore x is equal to 12 is the answer. Okay, but you need to write this because there's a chance that your like exam would have this and you might lose a mark for it. Okay, now that is not the final answer though. That's just the value of x. We now need to find the final length. So we're going to sub in. Sorry, sub. Go away. Okay. Sub x is equal, not 5 to 12. Okay, so L is equal to 5 times 12 plus 720 on 12, which is 5 times 12 plus 720 on 12, which is 120 meters. Okay, do I just leave it there? Unfortunately not. I also need to figure out whether it's actually a minimum. What if it's a maximum? I don't really know. So you have two choices. You can find the second derivative and work from there. Now, I just don't like differentiating all of these like negative powers. It's not a bad idea. You most definitely can, But I personally would rather just do the bucket hat test. So I'm going to do the bucket hat test, okay? This is going to save me time, at least for me. So x, f dash of x, and we will sub in 12, 11, 13, something like that. Okay, so we know that this is 0, but I'm going to check anyway, just in case. So 5 times 12 plus 720 on 12. Oops, wrong. I need to put it into the derivative. Derivative is 5 plus 720 on 12 squared, which is wrong because I need to minus it. Okay, 5 minus 720 on 12 squared is 0. Now we're going to substitute 11 instead of 12, and that is minus 115 on 121. And then we have to substitute for 13. Is 125 on 169. So it decreases and then it increases. So therefore we can say, therefore min at L is equal to 120 meters. Okay? Or we should probably write a full sentence because this whole thing's a bit of a wordy thing. So then we can say, therefore the minimum length required is 120 meters. Okay? Anyone else get that completely wrong? Let me know if I just got that completely wrong, because there's a chance. But yeah, if anyone else did get a different answer, please let me know.